So picking up with problem number 8, a symmetric top has principal moments of inertia I sub 1 equals I sub 2 does not equal I sub 3. It is fixed at one point and moves in a uniform gravitational field. Let the center of mass be a distance L from the fixed point. Part A, write the Lagrangian and Euler angles. Part B, identify two cyclic coordinates and their conserved momenta. Part C, reduce the motion to an effective one-dimensional problem for theta of t. Part D, derive the condition for steady precession. And Part E, determine the small nutation frequency about a stable processing solution. So this is a type of canonical type problem that's seen a lot. This type of problem, at least, similar. So this is a rigid body motion. And Lagrangian and Euler angles, part A. So phi will be the precession about the fixed vertical axis, the z-axis. Theta will be the angle between the symmetry axis and the upward vertical. And psi will be the rotation about the body symmetry axis. So with this convention here, the center of mass height is z sub cm equals L cosine theta. So V equals mg L cosine theta. And for a symmetric top, the body frame, angular velocity components satisfy omega sub 1 squared plus omega sub 2 squared equals theta dot squared plus phi dot squared sine squared theta. Excuse me. While omega sub 3 equals psi dot plus phi dot cosine theta. So the rotational kinetic energy is T equals I over 2 times the quantity theta dot squared plus phi dot squared sine squared theta plus I sub 3 over 2 quantity psi dot plus phi dot cosine theta quantity that's squared. So since V equals mgl cosine theta, the Lagrangian is L equals I over 2 times the quantity theta dot squared plus phi dot squared sine squared theta plus I sub 3 over 2 times the quantity psi dot plus phi dot cosine theta squared. And then minus mgl cosine theta. So the sign of the potential reflects the convention that theta equals 0 places the center of mass above the pivot, and theta equals pi places it below the pivot. Okay, so moving along to part B, identify two cyclic coordinates and their conserved momenta. Some people call it cyclic. So here we go with the cyclic. So cyclic coordinates here and conserved momenta. Lagrangian does not depend explicitly on either phi or psi. So phi and psi are cyclic coordinates, and a momentum conjugate to psi is p sub psi equals a partial derivative of L with respect to psi dot equals I sub 3 times the quantity psi dot plus phi dot cosine theta. So if we define a constant p sub psi equals lambda equals I sub 3 times the quantity psi dot plus phi dot cosine theta. We define it as that. So physically, lambda is the component of angular momentum along the body symmetry axis, and lambda is going to equal L sub 3. So our momentum conjugate to phi is here. So momentum conjugate to phi, p sub phi equals partial derivative of L with respect to phi dot. So p sub phi equals I phi dot sine squared theta plus I sub 3 times the quantity psi dot plus phi dot cosine theta times cosine theta. Okay, so using here p sub psi equals lambda, comma, p sub phi equals I phi dot sine squared theta plus lambda cosine theta equals mu. So physically, mu is the angular momentum, and over here, the angular momentum component along the fixed vertical axis. So mu equals L sub z. And solving for the precession rate, that's going to give us isolating phi dot. Phi dot equals mu minus lambda cosine theta over I sine squared theta. And the spin rate follows from P sub psi equals lambda, and lambda equals I sub 3 times the quantity psi dot plus phi dot cosine theta. So psi dot equals lambda over I sub 3 minus phi dot cosine theta. And psi dot equals lambda over I sub 3 minus the quantity mu minus lambda cosine theta times cosine theta over I sine squared theta. Okay, so moving along now to part C. So for part C, the effective one-dimensional problem for theta of t. So because the Lagrangian has no explicit time dependence, the total mechanical energy is conserved in E equals T plus V. So therefore we could say E equals I over 2 theta dot squared plus I over 2 theta phi dot squared sine squared theta plus I sub 3 over 2 times the quantity psi dot plus phi dot cosine theta squared plus mgl cosine theta. Now building on that, if we use if we use the following, sorry about that. If we use phi dot equals mu minus lambda cosine theta over I sine squared theta, and psi dot plus phi dot cosine theta equals lambda over I sub 3, then I over 2 phi dot squared sine squared theta equals quantity mu minus lambda cosine theta squared divided by 2I sine squared theta, and I sub 3 over 2 times the quantity psi dot plus phi dot cosine theta squared equals lambda squared over 2I sub 3. So E equals I over 2 theta dot squared plus the quantity mu minus lambda cosine theta squared over 2I sine squared theta plus mgl cosine theta plus lambda squared over 2I sub 3. So from there, the motion, that's going to reduce to I over 2 theta dot squared plus u sub EFF of theta equals E. And because lambda squared over 2I sub 3 is constant, it can be omitted from the effective potential without changing the theta motion. So here, just rearranging that. So from here, u sub EFF star of theta equals the quantity mu minus lambda cosine theta squared over 2I sine squared theta plus mgl cosine theta, and also we have theta dot squared equals 2 over I bracket E minus lambda squared over 2I sub 3 minus mu minus lambda cosine theta squared divided by 2I sine squared theta minus mgl cosine theta close bracket. And the turning points of the nutational motion occur where E equals u sub EFF of theta. Okay, that's part C. Moving along now to part D. So the condition for steady precession. So for steady precession, theta of t equals theta naught, and that's going to be equal to a constant. So theta dot equals 0, theta double dot equals 0. Let phi dot equals omega, capital Omega there, equal to a constant. And the Euler-Lagrange equation for theta is going to be d dt, partial derivative of L with respect to theta dot minus partial derivative of L with respect to theta equals 0. And since the partial derivative of L with respect to theta dot equals I theta dot, then I theta double dot equals partial derivative of L with respect to theta. So partial derivative of L with respect to theta equals I phi dot squared sine theta cosine theta minus I sub 3 times the quantity psi dot plus phi dot cosine theta times phi dot sine theta plus mgl sine theta. Okay, so building on that, using that I sub 3 here, so So building on that, using I sub 3 times the quantity psi dot plus phi dot cosine theta equals lambda, the theta equation becomes this: I theta double dot equals sine of theta times this quantity, bracket I phi dot squared cosine theta minus lambda phi dot plus mgl close bracket. Okay, so what we could say here is for non-vertical steady precession, sine theta naught does not equal 0, and I omega squared cosine theta naught minus lambda omega plus mgl equals 0. So this is a condition for regular or steady precession. It may also be obtained from u sub EFF prime of theta naught equals 0. And the precession frequency satisfies the quadratic equation I cosine theta naught omega squared minus lambda omega plus mgl, and that equals 0. So when cosine of theta naught does not equal 0, omega equals lambda plus or minus the square root of lambda squared minus 4I mgl cosine theta naught divided by 2I cosine theta naught. In a real steady precession solution requires lambda squared be greater than or equal to 4IM GL cosine theta naught. So for a rapidly spinning top with large quantity here for lambda, large magnitude lambda, the two roots correspond approximately 2 here. Omega sub slow is approximately mgl over omega. Omega sub slow is approximately mgl over lambda. And pardon me if I'm miscommunicating anything. The math works out. If I miscommunicate any variables, my apology. I haven't had any coffee today. Omega sub FAST, that's about lambda over I cosine theta dot. No. So the conserved vertical angular momentum for the steady state solution is here mu equals I omega sine squared theta naught plus lambda cosine theta naught, and the corresponding spin rate is psi dot equals lambda over I sub 3 minus omega cosine naught omega cosine theta naught. Sorry about that. A little off today. Okay, so part 8, we want the small notation frequency about stable steady precession. So let the inclination be slightly perturbed. Theta of t equals theta naught plus eta of t, where we have here the absolute value of eta is much, much less than 1. And the reduced equation of motion is I theta double dot equals negative derivative of u sub EFF with respect to theta. So expand the effective potential about the equilibrium theta naught. U sub EFF theta naught plus eta equals u sub EFF theta naught plus u sub EFF prime theta naught eta plus 1/2 u sub EFF double prime of theta naught eta squared, and on and on and on. So that's the pattern there. And building on that for steady precession here, what that's going to do is it's going to require, so steady precession is going to require u prime sub EFF theta naught equals 0. So the linearized equation, that's going to be this. Let me just shift this. So I eta double dot plus u sub EFF double prime theta naught eta equals 0. And so the small notation angular frequency is omega sub n squared 1 equals 1 over I u sub EFF double prime theta naught. So using mu equals I omega, sine squared theta naught plus lambda cosine theta naught in the steady precession condition, MGL equals MGL equals lambda omega minus I omega squared cosine theta naught. What we have here is the second derivative simplifies to omega sub n squared equals capital omega squared times the quantity 1 plus 3 cosine squared theta naught minus 4 times lambda over I omega cosine theta naught plus lambda over I squared. So omega sub n squared equals lambda over I squared minus 4 lambda over I omega cosine naught plus omega squared times the quantity 1 plus 3 cosine squared theta naught. And omega sub n squared equals capital omega squared sine squared theta naught plus the quantity lambda over I minus 2 omega cosine theta naught squared. So omega sub n equals the square root of omega, capital omega squared sine squared theta naught plus quantity lambda over I minus 2 omega cosine theta naught, that quantity squared. So what we could say here, the stability criterion is U sub EFF double prime theta naught is greater than 0, and omega sub n squared has to be greater than 0. And adding on to this, for a non-vertical regular precession solution, the expression above is a sum of squares and is therefore non-negative. The vertical sleeping top cases theta naught equals 0 or pi must be treated separately because the Euler angle coordinates and the effective potential expression involving 1 over sine squared theta become singular there. Okay, well that's all for problem number 8. Thank you very much and have a great day.